Okay, so we had discussed in the last video about how there is a third thing that we can check for normality if the first two things don't check out. Okay, so the first was if they tell us the population distribution is normal, then we can conclude normality. The second is if we don't know anything about the population distribution, or we know that it's skewed, but the sample size is greater than or equal to 30, we can incite the central limit theorem to infer normality. And then kind of our last resort is if we have the set of sample data and we make some type of a graph, could be a histogram, could be a dot plot like in this example, or a box plot, and if when we graph it we notice that there are not any outliers or there's no extreme skewness, then we can also infer normality. Now, something that you should note is if your sample size is greater than or equal to 30, then it doesn't matter if there are outliers or extreme skewness. You can use the central limit theorem to still infer normality. Okay. All right, so we had talked about that there's a formula called the standard error for the sample mean, okay, and that is given by this formula right here, okay. The big difference in that is we are swapping out what would have been the population standard deviation in the numerator there for the sample standard deviation, okay. And here's the formula that we're using to construct a one sample t interval to estimate a population mean. Okay, so we're actually going to try to walk through hopefully two full examples of creating these confidence intervals here today. The first one is talking about Oreos, Milk's favorite cookie here. It says for their second semester project in AP Statistics, Anne and Tori wanted to estimate the average weight of an Oreo cookie and to determine if the average weight was less than what is advertised. It mentions here that they selected a random sample, so I'm going to highlight that because that's definitely one of our conditions that we're going to want to make note of. They took a random sample of 36 cookies and they found the weight of each cookie in grams, and here's what they came up with. The average weight of their 36 cookies, the average weight, was 11.3921 grams, and the standard deviation for that sample was 0.0817 grams. Okay, the directions here are asking us to construct and then interpret a 95% confidence interval for the mean weight of an Oreo cookie. Okay, so our goal here is to try to estimate what is the true population mean weight of an Oreo cookie. And so when we break this down into our 4 steps here, the state step is where we are stating this is what the whole goal is. We are to estimate mu, and then we're going to define what mu is. That is the true population mean weight of an Oreo cookie. And then part of this state step is to say at what confidence level we want to construct this confidence interval under. And we're going to say at a 95% confidence level. Okay, so 2 pieces here that's very important. 1 is defining what it is we are estimating, and 2, at what the confidence level would be. Okay, that's the state step. Okay, there are also 2 overarching elements here to the second step, which is the plan step. One of those is that we state the specific name of the inference procedure. This is called a one sample t interval for means. Okay, you want to make sure you include all of these elements here to this. The one sample is because we did not, it didn't say Anne and Tori took 2 samples, which later we'll get to that in a later chapter. So this was one sample. We are using t-scores. T is very important here. Okay, interval, that is identifying the fact that this is a confidence interval, and we are estimating a mean here, not a proportion. Okay, so that's the first part to this, and then the other element of the plan step is for us to run down through our 3 conditions. We know those now, hopefully very well, to be random, 10%, and the normal condition. And so we need to show evidence and proof of each of these 3 things here. For random, we're just going to go ahead and reference what I highlighted here, that a random sample was taken. Okay, remember the 10% condition, that is what we use to conclude independence here. Okay, and we do that specifically when they're taking samples and they're not replacing in between drawing out samples, which they obviously would not be putting a cookie back in when they drew out these 36 cookies. So we're doing 10 times 36, that's 360. Certainly we could conclude that 360 is less than or equal to all of the Oreos in the Oreo population here. Okay, and now we're down to checking off the normal. Okay, remember this is not proportions. We are not doing the large counts condition. Okay, we have three possibilities. One is they told us somewhere in the problem that the population of Oreo cookies was normal, and I didn't read that anywhere, so I don't think we can use that. Okay, number two would be, could we do the central limit theorem? Is the sample size large enough? And look at what our sample size is. It was 36. So we want to identify the sample size is n equals 36. Well, that is greater than or equal to 30. And we can write down CLT, central limit theorem. Okay, now we can move on to our do step. This is where we actually take the information and put it into our formula. Okay, we know we start out x bar, which is given to us right here. Okay, plus or minus. Then we put the t-score. I'm going to leave a spot for that. We'll come back to that here. Times the standard error of the sample mean. Okay, which is the sample standard deviation that was given to us, I underlined that up above in blue here, divided by the square root of n, which is the square root of 36. Okay, now I need to get the t-score here. So I'm going to use inverse t. I also could use table B, but if I use inverse t, there are two inputs I need to put in and identify. The first one is the area in the left tail or right tail. Okay, we are doing a 95% confidence interval. That means we got 5% area left over, but if it's split between the two tails, I want to divide that by 2. Degrees of freedom, remember that is 1 less than the sample size. That would be 5. Okay, if I punch that into the calculator, it would reveal a t-score of 2.03. That is what I'm using. Okay, I did not use inverse norm. These are not z-scores as they were with sample proportions. These are instead t-scores. Okay, there I've got my confidence interval, and so I want to draw my conclusion here, and I definitely want to use context and that template that we hopefully now are so familiar with. And it starts out, we are 95% confident that the interval of 11.36 grams to 11.42 grams captures the true population mean weight of an Oreo. Okay. Now there was a second part to this. There's a part B down here below. It says on the packaging, the stated serving size is 3 cookies, which is 34 grams. Does the interval in part A, okay, provide convincing evidence that the average weight of a single Oreo cookie is less than advertised? Well, keep in mind, the weight that they gave you on the package is the weight of 3 cookies. So our confidence interval is capturing the weight, the average weight of a single Oreo cookie. And so that we're talking about the same thing, let's take the 34 grams, which represents the package's weight of 3 cookies. Let's divide that by 3. And so what they're really saying is they're advertising that the weight of a single Oreo cookie is roughly 11.33 grams. So let's look at their advertised weight. Let's compare that to our confidence interval. And let's see, does it look like that number is falling as a plausible value in our confidence interval? And I don't see that there. It doesn't look like it would fit in our interval. And so we're simply going to respond no, since 11.33 grams is not in the interval of plausible values. We're going to say there is not convincing evidence that the true average weight of an Oreo is less than advertised. Okay. In fact, all the values in our confidence interval were greater than what they are advertising. Okay. All right, let's go ahead and try just one more problem here. Very similar process our state plan do conclude. In this particular example, we're talking about the environment, and it says environments, government officials, vehicle manufacturers, they are all interested in studying the auto exhaust emissions that are produced by motor vehicles. There are major pollutants in these auto exhausts from gasoline engines. There's carbon monoxide, hydrocarbons, and one of the things that we're looking at in this example specifically is what's called nitrogen oxides that are being released by many of these engines, and we're going to refer to that as NOx, N-O-X. It says researchers collected data on the NOx levels in grams per mile for a random sample of 40 light-duty engines, all of the same type. Okay, so our sample size here is 40. That'll be important for us to note when we are trying to see whether we think the sampling distribution will be normal. It says the mean NOx reading was 1.2675, so I'm going to underline that. That's the average from the sample. And it says the standard deviation was 0.3332. Okay, the question is, they're asking us to construct a 95% confidence interval for the average amount of NOx emitted by light-duty engines of this type. Okay, so we're trying to come up with 95-degree confidence where we're estimating this true population average amount of NOx that's emitted. Okay, so in the state step, this is where we're saying, what are we trying to estimate? Well, we are going to estimate mu, which is the true population mean amount of NOx emitted by light-duty engines of this type, okay? Because it mentions up here, they took 40 light-duty engines, all of the same type, and so we can't necessarily be drawing this conclusion about all engines. That's why we want to be specific by light-duty engines of this type at a 95% confidence level. Okay, that completes our state step. The plan step, 2 pieces here. We want to name the procedure. That's our one sample. T interval for means. And then the other step is for us to run through our 3 conditions here. Okay, the first one is random. Okay, I'm going to say a random sample was taken. Okay, our second one is the 10% condition. That would be 10 times our sample size has to be less than or equal to all engines of this type. And it's safe to assume that there's more than 400 of these light-duty engines that are of this type. Okay, now our normal condition. Okay, remember what our sample size was. It was 40, which is greater than or equal to 30. Which means we can use the central limit theorem to go ahead and say that this sampling distribution would be approximately normal. Okay, now we are to the do step. So we're going to use, I had underlined these in orange up above, the sample mean, plus or minus, I'm going to leave a spot here for the t-score, okay, times my standard error of my sampling distribution, that is sample standard deviation in the numerator divided by the square root of the sample size in the denominator. To get my t-score, I'm going to use the inverse t feature. Remember, it requires 2 inputs, one, the area of one tail, and the degrees of freedom. Okay, degrees of freedom should be 39. This is a 95% confidence interval. So I'm going to take the extra 5%, split that in half, so I'm only talking about the area of one tail. That gives me a t-score of 2.02. Okay, my confidence interval is 1.161 to 1.374. So in my conclude step, I'm going to say we are 95% confident that the interval, and then we say the interval. And I'm going to label this because, you know, we want to give some meaning here to these numbers. Okay, up above here, these NOx levels are measured in grams per mile. So it's from 1.161 grams per mile to 1.374 grams per mile. Okay, that captures the true population mean amount of NOx emitted by these light-duty engines. Okay, and there was one second part to this. It said the Environmental Protection Agency sets a limit of 1 gram per mile on average for NOx emissions. Can't go over that, okay? Or it's just damaging the environment way too much. It says, are you convinced that this type of engine violates the EPA limits? Well, let's look and see here. Use our interval in Part A to support our answer. Well, look at all the values here. They're all above what the limit is of 1 gram per mile. So I'm going to say, yeah, there is convincing evidence that this type of engine violates the EPA limits. Okay, and I have to say why. You can't just make that statement and not have a justification. So I'm going to say, since all the plausible values in the interval are greater than the 1 gram per mile that the EPA set. Okay. All right, I do want to show you how you can do these problems on the calculator. It says, can you use your calculator for the do step? And I really want to stress this, that if you are going to use your calculator, it only replaces the do step, and that is it. It does not replace you listing all the state stuff, the name of the interval, your conditions, or your conclusion. Okay, where you're going to go on the calculator is you're going to hit that stat button and you're going to bump over to the test button, and you're going to pick from there, I believe it's called T interval, okay, T interval. Okay, when you pick that, there are two options. One says data and one says stats. In this example, you would pick the stats because you don't have the body of data. All you have are the mean and the standard deviation. So you would pick stats. What you would have to write down, though, is you have to write down all the inputs that you are putting into your calculator. Okay, so you would put down what you're typing in, 1.2675. You would be putting in, what is this, 0.3332. Okay, you would put in your sample, anything it asks you, this is what you put down. Okay, you put your confidence level, and then the other thing you have to report is you have to report the degrees of freedom. You absolutely have to do that. And so that is 39, okay? When you do that, it's going to spit out a confidence interval, and guess what? It's going to be the exact same confidence interval that you would have gotten had you used the formula. And so essentially, you're replacing showing this formula and maybe this part here with just listing all your inputs that you're putting into the calculator, and it will spit out your confidence interval. Okay, we will pick up